Swayam Prabha. Digital India. Educated India.
Good morning. In the previous lecture, we studied solution of systems of ordinary differential equations. Today, we will apply that knowledge, apply those methods to the problem of stability analysis of dynamic systems. At length, we will discuss the special case of second order linear systems, because of two reasons. One reason for why second order, and the second reason for why linear. As I outlined in the last lecture, a predominant number of dynamic systems appearing in nature follow a second order dynamics, and therefore the analysis of second order dynamic systems becomes very important. And apart from that, up to second order analysis is to a good extent possible, and a lot of analysis is possible because you can show that analysis on a piece of paper. Any plot that you make on a piece of paper, or the one that we will make on the blackboard once in a while, all of that is actually two dimensional. So, if we have two state variables, then we can represent the behavior of the dynamic systems in a two dimensional plot. Now, why linear? Because it is first of all easy to analyze linear systems to a great extent. For nonlinear systems, the analytical procedures get blocked after a point. So, for linear systems, we can analyze to a great extent, and theoretical predictions or theoretical study which have far reaching consequences, we can draw in a major way in case of linear systems. And many actual systems are either linear, or to a good extent they can be approximated by linear approximations. Therefore, the second order linear systems have got enormous amount of research focus for quite a few centuries, and the basic facts, basic analysis regarding the stability of second order linear dynamic systems is what we will consider for the major part of this lecture. And after that, we will consider a few issues regarding higher dimensional or higher order systems and nonlinear systems, how we go about stability analysis of those systems beyond second order and beyond linear. So, first we go to second order linear systems, and among them particularly we will consider the autonomous systems, second order autonomous linear system. Now, the point is that why we are considering autonomous? Because stability analysis will make particular sense in the case of autonomous systems, where there will be certain equilibrium points around which we will discuss the issue of stability. So, suppose we take a system of two first order linear differential equations like this. Now, note that we are talking about second order, but we are actually considering two first order differential equations. Now, there is no discrepancy here, there is no mismatch in the two issues, because a single second order differential equation can be always broken down into two first order differential equations, as we do in state space. So, in state space, a single second order differential equation will also be broken down in this manner, in which there will be two state variables. So, whether the system originally consists of two first order differential equations or one second order differential equation broken down into two first order differential equations, for our purposes there will be no difference between the two. Now, in this case we have this vector equation in which this entire thing has been written together, and here the matrix A is 2 by 2, and we have got a system of two first order linear homogeneous differential equations which are with constant coefficients. So, a11, a12, a21, a22, these are constant. Now, and it is autonomous also. So, anyway these things had to be constant. In the case of second order systems, a lot of terminology got developed when this entire study was in the hands of people who were primarily physicists, and quite a few words related to phase have entered into the jargon. So, in this kind of a situation, phase means a pair of values of y1 and y2, that is actually the state, what we otherwise call state. In this discussion quite often we will be calling it as phase. So, one value of y1 and one value of y2 consists of one state of the system, and in this discussion quite often it is also referred to as phase. Now, if we plot y1 in one of the axes in our graph paper and y2 along the other axis, then the plane in which we will be making the plots, that plane is called the phase plane, the plane of y1 and y2. Now, in the phase plane, in the plane of y1 and y2, from one point if we start, and then that can be considered as the initial condition for the system of differential equations, and then from there if we draw a curve which obeys these differential equations, then that curve is called a trajectory. That is, as we consider the independent variable as time, then this curve, this so called trajectory, will show along which path in the phase plane the system will evolve. So, this trajectory is a curve showing the evolution of the system for a particular initial value problem. That initial value is demarcated by the initial point with coordinates y1 and y2, which we can put at a point. Now, in the phase plane, then if we start from say this point, then the curve can go in some way. So, this will be a trajectory. Now, if there is another point from where we start, we will get some other trajectory. If we start from another point, we may get some other trajectory, right. Now, these trajectories, when we put all trajectories, that is a number of trajectories which will represent all trajectories in the sense that how much is the density of trajectories you plot, that is up to you, but if you go on plotting dense enough set of such trajectories, then together they will show the dynamic behavior of the system starting from all possible initial conditions. So, that picture is called the phase portrait, all trajectories together showing the complete picture of the behavior of the dynamic system, that is called the phase portrait. Now, in this analysis we will be considering the case of non-singular A, that means no degeneracy, only the non-degenerate case as we did last time in the previous lecture. Similarly, here also we will consider non-singular coefficient matrices in this place A. So, that will mean that the equilibrium point will be only isolated equilibrium point, and in this particular case where it is linear homogeneous, then the only equilibrium point possible will be the origin, because with non-singular A, ay will be 0 only at y equal to 0, that is y1 equal to 0, y2 equal to 0. This will be the only equilibrium point, and around that if we can complete the analysis, then in a way we would have finished the analysis for this particular system. So, we will be allowing isolated equilibrium points, and matrix A is the non-singular, origin is the only equilibrium point. And then how is the behavior of the dynamic system around this equilibrium point will be governed by the eigenvalues of this, right, because the two eigenvalues will give us two components of the solution, both exponential in general, and then the combination of that, the linear combination of that will show the complete behavior, right. So, if we try to find out the eigenvalues of this matrix, coefficient matrix, then as you know, we will be first trying to solve this, right, and from there we will get a quadratic equation in lambda. So that quadratic equation will be this minus this, right. So lambda square minus the sum of these two, lambda plus this product minus this product, equal to 0. So this will give us the characteristic polynomial characteristic equation, and that is what we have got here, right. Now we will represent for a particular reason this sum as P and this quantity, this value as Q. That means this is the trace and this is the determinant of the coefficient matrix. So trace of the negative of the trace, negative of the trace of the coefficient matrix is this, that will be representing as P, and this determinant will be representing as Q. As we do that, we get this as the characteristic equation, right, with P as A11 plus A22, which is the sum of the eigenvalues, and Q, which is the determinant, which is the product of the eigenvalues. Now we will consider different cases that may arise. We know that discriminant of this quadratic equation is P square minus 4Q, and depending upon whether this is positive or negative, we have different cases of the way we will get the two eigenvalues. Now first consider this issue, that is, of course the two lambdas will be given by this standard formula for the quadratic equation solution. Now a particular case where Q is negative, that is the two eigenvalues product, the product of the two eigenvalues is negative, that is a situation where this discriminant is always positive, because this is P square. Now if Q is negative, that means this whole thing is certainly positive. Okay. Not only that, it is positive and it is larger than P square. Why is that important? Because in that case this D will be positive and its square root will be larger than the magnitude of P, and that will mean that this term, which will be root D by 2, will be larger in magnitude than P by 2. Now this term in the two eigenvalues will appear with opposite signs, plus and minus. Now if this term has larger magnitude than this, then that will mean that when we take the plus sign, this entire value will turn out to be positive. This fellow P by 2 of whatever sign cannot dominate this. So the sign of the lambda, sign of the eigenvalue will be dominated by this term, because root over D is larger in magnitude compared to P. So when we take the positive sign, we get the positive root, and when we get the negative sign here, we get the negative root, because this fellow, this term will not be able to dominate over that. So in the case of negative Q, two things will happen. One, that this will be positive and therefore the roots will be real, and this will dominate over this term, and therefore two roots will be of opposite signs. So when we have that, two roots will be of opposite signs. So now in that case we have got this. Now there are two different roots, distinct roots, so obviously it is diagonalizable matrix. So in that case we get the two solutions like this. Now note that one of them is positive, the other is negative. Now the two corresponding eigenvalues, eigenvectors, one is x1, the other is x2. Now if lambda 1 is larger, that will mean that, and that is say now one will be positive, the other will be negative. Now if one is positive and the other is negative, that means with time the positive one will grow that means its magnitude e to the power lambda 1 t will go on increasing exponentially, and in that case this one will go on decreasing exponentially, and that will mean that around origin, note that we are discussing the behavior around origin, because if the initial conditions are given at origin, then the system will remain there. That is the characteristic of equilibrium points anyway. Now around origin, whatever point we take and we put that point in this plane around origin, near origin, somewhere here, and in that case if the two eigenvectors x1 and x2 from here have two directions, now one eigenvalue is positive, so around that direction whatever little solution, whatever value is there, whatever initial condition is there, that will keep on growing. Okay. So along that direction the motion with time will go on increasing. So whatever is the initial position, as we decompose that along the two eigenvectors, the component along the eigenvector with positive eigenvalue will go on increasing with time, and the component along the eigenvector corresponding to the negative eigenvalue will go on decreasing with time, and that means that over time the trajectory will get aligned with the larger the positive eigenvalue. So see here, this will be the case. Now if these are the two eigenvectors, then if we start from here, then with parallelogram law we can decompose the position vector of this point into two components. One will be along this direction, along which the eigenvalue is negative, that means trajectories come in, and the other component will be this one, this much, and that is corresponding to positive eigenvalue, along which the trajectory go out. So that means this component will decay and this component will grow, and that is why wherever we start, if we start here, then the component along this will decay, so it is coming like this, and the component along this will grow, so it is growing like this. So all trajectories will move away and finally along this direction, and it will get, as it goes far away, the trajectories will get all bunched together with this. So the further away they are, that much will be the difference. The two trajectories will not cross, but all of them will get bunched along this, and if the starting point is below this line, then they will get bunched along this, either forward or backward. So all trajectories eventually will go in this direction and go away from the origin. That means that this is an unstable equilibrium point. So this particular equilibrium point in that kind of a situation is unstable, because if we start a little away from the equilibrium point, a little away from the origin, then the trajectory diverges further and further away from the equilibrium point. So that is the hallmark of an unstable equilibrium point. So if q is negative, and in that case we get two real eigenvalues of opposite sign, and in that case certainly the equilibrium point is unstable, and such an equilibrium point is called a saddle point. Okay. So one eigenvalue positive, the other eigenvalue negative. Now other than that, if q is positive, then what will be the situation? Note that q equal to 0 case is not under discussion, because q equal to 0 would mean that lambda equal to 0 is one solution, which is the case when A is singular, and that will mean that one complete subspace will be equilibrium points, and that case we have omitted. So q equal to 0 case is not in our discussion at all. So in the case of q negative, we will get saddle points which will be always unstable. Now if q is positive, now one point is easy to note, that the nature of the equilibrium point will be the same irrespective of the sign of p, because p is appearing here as p square, right. So it will be symmetric with respect to the sign of p. So let us consider p square equal to 0, larger, 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 and so on. So with q positive, if p square is 0, that is p is 0, if p is 0, then what we are getting? We are getting d as minus 4q and p is 0. So, if p is 0, then this goes off, and here we have got a negative discriminant. That means the eigenvalues will be pure imaginary. So, if eigenvalues are pure imaginary, that is plus minus omega I kind of eigenvalues, that will mean that when you decompose that exponential e to the power I omega t, okay, plus I omega t minus I omega t. So, you will get basically cosines and sines. So, you will get sinusoidal output, and in that case you will get this kind of behavior. So, around that equilibrium point, the trajectories will make a closed curve, and such an equilibrium point is called a center, right. So, this is stable because started close to the equilibrium point, the trajectory will remain close to the equilibrium point, it will never go too far. Now, where you start, at that point whatever is the distance, compared to that the distance might increase, but it will again decrease because it is a closed curve. So, this is one particular case, that is if p is 0. Now, if p is greater than 0, that is if p is positive or negative, say p square is positive. Now, when p square is positive, then whether p square is less than 4q or greater than 4q, these two situations will give rise to two different kinds of equilibrium points. If p square is positive and less than 4q, then this discriminant is nevertheless negative. So, this is negative. Okay. So, in that case you will, but then this is not 0, this is not 0. So, there is a non-zero part here and this is negative. So, it will be a full fledged complex number with non-zero real and non-zero imaginary part, and in that case you will get eigenvalues which will be like lambda equal to mu plus I omega t, mu plus minus I omega. So, in that case the solution, this solution, these two solutions. Okay. So, what you do in that type of situation, you reorganize the coefficients and say the solutions will be, one solution will turn out to be like e to the power mu t cos omega t, and the other will be e to the power mu t sin omega t. Now, this cos omega t sin omega t term will try to give an oscillatory feature. However, this e to the power mu t part will give the amplitude as variable, the amplitude will be exponential, right. So, in this kind of a situation, what you will have is that whether this mu is positive or negative, according to that this solution, both of them together, will grow or decay, right. So, that sign will be determined from here, because in this case this is the only exponential part, this part will give you this sinusoid. Okay. So, the exponential part will grow or decay depending upon whether p is positive or negative. In any case, it will be, if it grows, then and this part will provide an oscillatory component, right. So, you will have either this going inward, amplitude decreasing if mu is negative, and if mu is positive, then along a similar curve the spiral will go out, and because of obvious reasons this kind of an equilibrium point or critical point is called a spiral. Now, we come to another situation, that is if p square is greater than 4q. If p square is greater than 4q, then this d is positive. However, with positive q, its value, its absolute value will be less than this part, okay, because q is positive. So, p square minus 4q is certainly less than p square. So, therefore, its square root, even if positive, will be certainly less than p in magnitude. Okay. So, that will mean that this plus minus sign will not play a role in the final sign of lambda. So, final sign of lambda 1 and lambda 2 will be decided by the sign of p. So, if P is positive, then whatever large is this, it will be certainly less than this term. So, then the total will be positive anyway. Similarly, if P is negative, then even the positive sign taken here will not be able to make the sum as positive. So, the sign of this entire lambda will be determined by this and not by the plus minus term, and therefore, both of them, both of the eigenvalues will be of the same sign, either both positive if P is positive or both negative if P is negative, and that will save the solution from this kind of a situation where one grows and the other decays. In this case, if P is positive, then both will grow, and if P is negative, then both will decay. So, that kind of a situation with the two eigenvalues having different magnitude will give rise to this situation. You see, here there are two eigenvalues, correspondingly there are two eigenvectors. This is one and this is another. In this case, the sign of P has been taken as negative for this particular plot. In this plot, in all cases, wherever it is possible to have a stable situation, we have drawn the stable case in all these cases. Okay. So, here both the eigenvalues have negative real parts. So, this eigenvector also comes inward, this eigenvector also comes inward. But then if one of the eigenvalues is large, that means that the rate of approach for that particular eigenvector, say e to the power 70 and e to the power 2t. So, this one is large, this one is small. So, as t grows, of course, you have negative if you follow this particular kind of plot in which the arrows are inward. Okay. So, this is e to the power minus 70, this is e to the power minus 2t. Now, this one will decay much faster than this, and therefore, you see that the component along this one will decay much faster. So, from here the component is this big, but this is decaying much faster compared to this component. So, the component along the larger magnitude eigenvalue will decay extremely fast compared to the other one, and therefore, finally, all the trajectories will become tangential to this line. Okay. And this is called an improper node. There are various other cases of nodes. Now, this is the situation where the two eigenvalues have different magnitudes. Okay. Now, with the same sign, if the sign is positive, then along the similar trajectories the system will evolve outward, and in that case it will be unstable. In the case which you see here, it is stable. Just like spiral, it could be outward rather than inward, similarly here also. Now, this is called an improper node. If P square is exactly equal to 4q, then what happens? Then D is 0, and then you have got both eigenvalues same, P by 2. Now, depending upon whether P is positive or negative, you will have the eigenvalues positive or negative, but both of equal magnitude as well as sign. So, two equal eigenvalues. Now, when the two eigenvalues of the matrix are equal, then you ask whether the eigenvectors are a full set of two eigenvectors or only one eigenvector is there, because with repeated eigenvalues the canonical form could be this, or the canonical form could be this. In this case, there will be two eigenvectors linearly independent, which will mean that the entire plane is composed of eigenvectors. All vectors along the plane, on the plane, are eigenvectors in this case, right. However, in this case there will be a single eigenvector. Now, if you have got both eigenvectors, that is, if the matrix is diagonalizable, then all directions are eigenvectors, and along all directions the behavior will be same, and in that case you have got this situation, and this is called a proper node. So, wherever you start the system, whatever initial condition you give, the system will evolve directly towards the origin in the case where this lambda is positive, negative. On the other hand, if this lambda is positive, then from wherever you start, that is an eigenvector. So that position vector, initial position, initial state vector is an eigenvector. So along that, with positive lambda it will straight go out, if with negative lambda it will straight go in. So this is called a proper node. The last case where you have got p square equal to 4q, that means d equal to 0, that means lambda, both lambdas are same, repeated eigenvalue, and the matrix is not diagonalizable. In that case, as we have found that in the case of non diagonalizable coefficient matrix, you get this solution y, from which you can determine y prime, and you get situation like this. And here you see there is a time element coming here, okay, in the coefficient here. So from that, if you analyze, then you will find a very peculiar situation of the phase space. If this is a single eigenvector, then all the solutions will approach along this eigenvector only. There is only one eigenvector, so all of them come like this. In the case of negative eigenvalue, it will come like this inward. In the case of positive eigenvalue, they will go outward with the arrows reversed. So this is called a degenerate node. So what are the types of critical points or equilibrium points we found? With real eigenvalues with opposite signs, we have got saddle point, which is always unstable, and with pure imaginary eigenvalues, we have got center, which is always stable, but this is a borderline case, because any modeling error and it might fall in the case of spiral, that is any modeling error and p turns out to be actually a little positive or negative, that will mean there will be an outward unstable or inward stable spiral. Now this is the case from p square equal to 0 to 4q, greater than 0 and less than 4q. P square equal to 4q will give these two cases, okay, both eigenvalues same, and eigenvectors, both eigenvectors existing, only one eigenvector, proper node, degenerate node. And in the case of p square not equal to 4q, that is p square larger, you have got two eigenvectors, two unequal eigenvalues of the same sign, and in that case you have got improper node like this. A summary of all these cases you can see here in the table and also in this plot, in the plot of PQ. So you see with Q negative, this entire part gives you saddle point, which is unstable. Q equal to 0 case we have discarded because that is singular coefficient matrix. With Q positive, that is upper half of this PQ plane, you have got this saddle point is real opposite sign eigenvalues Q negative, so it is always unstable. Above the P axis with P equal to 0, you have got this line along which you will get center, and eigenvalues are pure imaginary. This is the case which is stable. In the case of the PQ point lying above this parabola P square equal to 4q, you have got spirals, right. So eigenvalues are complex and both real and imaginary parts have non-zero components. So you get here negative P stable spirals and positive P unstable spirals. So with P equal to negative, you get unstable stable points here, and with P equal to P positive, you get unstable, whether it is spiral or node. So in the case of nodes, you have got several cases, all with real same sign, okay. So they are stable if P is negative, unstable if P is positive, just like spirals. And here if the eigenvalues are unequal in magnitude, that will mean D is positive, that means you are here, okay. And if you have got, you are on the boundary, that is P, it is on the PQ point is on this parabola, then that will mean one of these two cases. In the diagonalizable case, you have got a proper node. In the deficient case, you have got a degenerate node. So this is the complete breakdown of all the types of equilibrium points that you can have in a second order linear system. Now when you get a non-linear system, say, then what you can do is that around every critical point that you get, you can conduct an analysis of this kind and find out how the trajectories around that point will behave, and then you can compose the situations around all the critical points together to complete the phase portrait. So, for a nonlinear system where you will have the differential equations of an autonomous system in this manner, then first you will try to find out critical points or equilibrium points, and for a nonlinear system origin may not be a critical point, and apart from that you will typically expect more than one critical point. Origin may be a critical point among them, but there will be expected other critical points as well. So, what you will do? You will first solve Fy equal to 0 and collect all the solutions of it. For each solution of it, say call it y0, then around y0 you will conduct a linearization and you will capture the first order behavior of the system around every critical point with this kind of a differential equation, which is linear. Now, as you put y minus y0 as z, then you will have z prime is equal to this Jacobian j into z, and then this will be a kind of a system which we just analyzed. So, you can make the phase portrait of this system and take that portrait, a small part of it, a small part, because this is first order analysis and will be valid only in the neighborhood, and that you can plug in at y0 in the y plane, and similarly at every y0 you plug in a small phase portrait which you get through the analysis of this kind of a system, and then you can try to assemble the entire phase portrait of the original system. So, through the assembly you will find that you are able to picture the entire phase portrait even for the nonlinear system. So, that shows that features of a dynamic system are typically captured by its critical points and their neighborhoods. Let us take a small example. Say we consider this population model of a pair of competing species who depend on similar resources. So, suppose x and y are the populations of the two species as functions of time, and the dynamic system is given like this. Each term here with its coefficient has a meaning. This coefficient A represents the rate of reproduction and growth of species X, that is its inherent rate of growth, positive. Now, this B represents the result of intra-species rivalry between members of this same species X. So, that is why it is the intra-species rivalry basically depends on two individuals, and the more number of individuals that are available as the first party of the rivalry will make the rivalry sharper. Similarly, more number of individuals available to form the second party in the rivalry, that will also make the rivalry even sharper. Therefore, it depends upon x square, is proportional to x square, and this term comes as with negative sign, because of the intra-species rivalry where both individuals from the species will try to corner the same resource. So, that will in some way lead to decay of the species, because they are fighting within themselves to corner the same resource to grow. Similarly, this term shows the effect of interspecies rivalry with the other species trying to corner the same resources. So, this capital C represents the effect of interspecies rivalry with the other species, its effect on the first species. Similar coefficients a, b and c, small a, b and c will represent the similar actions for the second species. This is small c. Okay. Now, with this you can see that this is a nonlinear system, right. Now, if you denote r as the vector x y, then this f of r will have two components, this and this. Okay. So, r prime will be f of r, which will have these two components. Now, what will be the Jacobian of this? Jacobian of this you can find out, and before that you can try to find out what are the equilibrium points. Which are those points where if the population is from the beginning at a particular time t equal to 0, then the population will be constant, will never change. What are those equilibrium points? So, for that you can solve these two equations and find out those equilibrium points. So, if you solve these two equations for x and y, you will get the solutions as one solution is origin obviously. So, you will find the solutions are origin, a by b 0, 0 small a by small b, and the fourth one is complicated, ab minus ca divided by bb minus cc, ba minus ac divided by bb minus cc. So, these are the 4 equilibrium points. You can verify very easily. 0 0 will obviously, and these are 2 quadratic equations. So, in total they will have 4 solutions. So, origin is obviously a solution. Now, if you take y equal to 0, then this term goes off, this term goes off, okay. And then from here you will get x as capital A by capital B, okay, and y is 0 of course. So, that is this. On the other hand, if x is 0, then this is 0, this is satisfied, okay, and sorry, these are y. So, if y is 0, then this is satisfied and this is 0. So, x is a by b, and if x is 0, then this is satisfied anyway and this is 0. So, y will become small a by b, that gives you this. If neither x nor y is 0, then the solution is a little complicated, but you can see that substituting this you will find that these two equations are satisfied. So, these 4 points will fall here, origin, capital B by capital A 0, 0 small a by small b, and the fourth one will be somewhere here. Okay. Now, around origin, if you if you can find out the Jacobian matrix, so you will basically differentiate this with respect to x and get a minus 2bx minus cy, this is x derivative. Now, the y derivative of this will be minus cx, then x derivative of this will be small minus small c y, and y derivative of this will give you this. Now, you see at each of these 4 equilibrium points you can find out the value of the Jacobian, and then for every such point you will get the differential equation system up to first order as y minus that equilibrium point, any of the 4 you can put there, this multiplied with the j at that point, okay. This will be z prime, that is y prime minus 0, that is y prime itself. So, y prime and z prime will be same. So, you can put it like this. So, around each of the equilibrium points you can find out the value of the Jacobian by putting the x y coordinates of that equilibrium point and frame a linear system and analyze. You will be able to see very easily that this point is a node, is an unstable node, and because as x and y you put as 0 0, then this matrix will be a 0 0 small a. Okay. So, this will be a node. Okay. Both eigenvalues will be positive. So, it is an unstable node. Why? The logically you find that if the initial populations of both of them are not 0, that is, if any one of them or both have any non-zero, small non-zero population, that will mean that at that time the resources are aplenty, because the members in the two species are very small. So, lots of natural resources around. So, they will go on consuming those resources and grow, and at that time with small x small y values, these terms anyway will not play a major role, these will be dominant, right. So, growth of both will be supported. Of course, the one which is of larger growth rate, depending upon whether capital A is large or small a is large, that will grow faster. In any case, both of them will grow. So, you see that suppose capital A is large, that means around for this the growth will be faster. So, that means that all trajectories will start moving like this. Like this, okay, improper node. Now, at this point, what is happening at this point? At this point, you will find, let us mention the Jacobian here. I will give you the Jacobian at this point. The Jacobian at this point we had simply this, right. At this point, the Jacobian turns out to be minus a minus C a by b 0 and a minus C a by b. Now, for this Jacobian you can see very easily that 1 0 is certainly an eigenvector of this matrix. Try to multiply this matrix with vector 1 0, you will get minus a plus 0, and in the lower one you will get 0 plus 0. That means, if you multiply this with 1 0, you will get minus a 0. 1 0, that means 1 into this plus 0 into this. So, you will get minus a 0. So, that means minus a is the eigenvalue and 1 0 is the eigenvector. So, at this point this is one of the eigenvectors, and along that the eigenvalue is minus a, and that shows that this point along this direction at least is stable. Now, what is the situation along the other direction, along the other eigenvector, and that could be positive as well as negative depending upon what is the other, what are the values of these coefficients. Okay. So, one possibility is that this is the other eigenvector, and that means that if along this it goes in, then along this it goes out like this. Similar could be the situation here. This will be one eigenvector and this could be the other eigenvector. So, along this it will go in, along this it will come out, along this it will go in, along this it will come out. Okay. So, you see that these directions, these trajectories might meet here, because at this point as you come, it could be an inward node, that is stable node. So, try to analyze this particular case. The analysis is there in the book. Try to in the textbook that we are discussing, we are considering. So, the entire analysis is there in the book. So, as you consider different cases, you will find that if you draw the phase portraits around these 4 equilibrium points, and try to assemble together, you will find that you will get the complete picture of the phase portrait of the system. Now here we will raise another question other than the nonlinearity. One question within nonlinearity and another question apart from nonlinearity regarding dimensions. There is one particular feature which is not covered in the analysis here. Here we found saddle points, center, spiral, node, these kinds of equilibrium points. Now linear systems can have only this much, only these many features, such points they can have. There is something else which is possible in nonlinear systems. Nonlinear systems also will have in certain points, equilibrium points, which are nodes, saddle points, spirals and center points. But apart from that, in the case of nonlinear systems, there is another feature which is possible, that is called limit cycle. And in that case, you have isolated closed trajectories. This is not like center point. Around center point is one equilibrium point around which there are trajectories which happen to be closed. Now limit cycles are completely different. The entire closed trajectory is such that the entire trajectory behaves like a equilibrium point kind of thing. Okay. So this kind of a feature, this kind of a situation can arise only in nonlinear systems. In chapter 29, in one of the exercise problems, this example exercise 29.2, the exercise simply is an exercise on numerical solution of one second order differential equation. But then if you analyze it for enough time, or if you study the solution of that particular exercise given in the appendix of the textbook, you will find that this case gives you a limit cycle, and that shows that if you start from outside the limit cycle, say the limit cycle is a closed trajectory like this, and if you start outside, then this is the trajectory, and finally the trajectory merges on the limit cycle, does not go in. On the other hand, if you start from inside, say from here, then you go outside and then you merge with the limit cycle and do not go out. Okay. So this cycle, this closed trajectory is called a limit cycle. That kind of a thing is possible only in the case of a nonlinear system. This particular example of exercise 29.2 is this nonlinear differential equation. This is a nonlinear, see this is the nonlinearity here. Okay. So this nonlinear equation will give you a limit cycle of this kind. So limit cycle is one feature of nonlinear dynamic systems which the linearized analysis will not be able to capture. Okay. Now one more issue. What do you do in systems, in the case of systems with higher dimension of state space? There straightforward phase plane analysis you cannot conduct. However, you can always try to linearize the system of equations around every equilibrium point like this, and then conduct linearized analysis and then try to work out the features. Now in the case of nonlinear systems, quite often you might find that in one subspace of the state space you get a spiral like feature, while the other subspace shows a node like feature. So that kind of a situation is possible. So such things might happen in the case of higher dimensional state space. There is another technique of analysis of stability for nonlinear dynamic systems, and that is the famous Lyapunov stability analysis. There are quite a few important terms associated with Lyapunov method. The precise definition of stability here is this. if y0 is a critical point of the dynamic system, this, and for every positive epsilon, if there exists a delta such that the initial point taken within a delta distance of the critical point keeps the system always within an epsilon distance, then you say that the critical point y0 is stable. What is the idea here? That is, if you prescribe epsilon, that is, if you say that will your system remain within this much distance of the critical point, then you answer that yes, it will remain if you start sufficiently close, say within delta distance. If you can say so, that if there exists a delta such that, if you can say, if you can prescribe such a delta for every given epsilon, then you say that this point y0 is a stable critical point. That is, if you can keep the system close enough by starting close enough, then it is a stable critical system, a stable critical point. There may be situations where whatever close you start, eventually you will go far away from the critical point, then that critical point is called unstable. Okay. So, this is the criteria for stability. If further, not only that it stays close, if as enormous time is passed, eventually if the point y0 is approached, then you call that point as not only stable but asymptotically stable. You would be able to see that in the earlier case, stable nodes and spirals were asymptotically stable. On the other hand, center points, which were always stable, were stable but not asymptotically stable, because in that case the trajectory does not approach the critical point. In the stability analysis due to Lyapunov, there is another important issue, there is another important term, that is the positive definite function. A function with value 0 at the origin, if it is always positive for non-zero points, that is away from origin, then that is called a positive definite function, as we know positive definiteness in general. What is a Lyapunov function? A positive definite function of the state vector having continuous partial derivatives with a negative semi-definite rate of change. That is, if v is positive definite function, but if its rate of change with respect to time, with respect to the independent variable t, is negative definite or negative semi-definite, then you call it a Lyapunov function. This is a Lyapunov function is actually an abstraction of the concept of energy in physics. So, energy can be considered as a positive definite function, total energy, and then the way the system evolves is in order to decrease the total energy. So, its rate of change with respect to time is negative. It could stay at constant for that matter, that is v prime could be 0. So, that is why semi definite is there. So, this kind of a function which is positive definite function of y, but its rate of change with respect to the independent variable t is negative semi definite, such a function is called Lyapunov function. With this kind of a definition, the actual stability criteria becomes quite straightforward, and that is the theorem. That is, for a system like this with the origin as a critical point, if you can construct a Lyapunov function which is positive definite with a negative semi definite rate, okay, then you can conclude that the system is stable at the origin. Okay. Further, if v prime is not simply negative semi definite but negative definite, then that will mean that energy will not only be non increasing, but it will actually decrease, and in that case you can see that the trajectory will actually approach the critical point, and in that case it is asymptotically stable. So, it is actually a generalization of the notion of total energy. So, negativity of its rate will corresponding to trajectories tending to decrease this energy. Now, Lyapunov's method is important because in the nonlinear case, or in the higher dimensional state space case, or in those cases where the linearized version of the state space of the state equation, if the linearized version of the state equation is unable to allow any analysis, in such cases Lyapunov's method turns out to be a useful method for analyzing the stability of a nonlinear system. However, caution should be exercised in using this Lyapunov analysis, because it is a one-way criterion only. If you can construct a Lyapunov function, then you can say that the system is, the origin is a stable point of the system. But if you fail to construct a Lyapunov function, that does not mean that the system is unstable. So, it is only a one-way criterion. So, in this lesson, the important issues that we have studied are analysis of second order systems, critical points of different kinds, and nonlinear systems with their local linearization to describe the system, and phase space analysis, which has enormous application in branches of science, physics, engineering, economics, biological and social processes. So, this in a way completes one module of our course. From the next lecture, again we will go back to solution of differential equations, certain situations where analytical methods fail, but much better than numerical methods we can use, and that is series solution. So, next lecture we will start series solution, and in that continuation we will slowly move from the study of differential equations to approximation theory. Thank you.